I want you to start off today by doing a little mental exercise with me. Just, picture our solar system.
Right, the classic textbook image.
Exactly. You've got the sun sitting right there in the middle, doing its thing. Then you have the inner rocky planets. So Mercury, Venus, Earth, Mars.
All the familiar ones.
Yeah. And then past that, you cross the vast rocky expanse of the asteroid belt. And finally, way out there in the freezing dark, you hit the massive gas giant Jupiter.
Which is incredibly far away.
It is. I mean, it takes light from our sun about 43 minutes just to travel that distance to Jupiter.
Which is a huge gap.
Right. Now, I want you to imagine taking a single different star and dropping it right into the center of our solar system where our sun currently sits.
Okay, I can picture that.
If you put this specific star in that spot, its surface wouldn't just swallow Mercury. It wouldn't just incinerate Venus and Earth and Mars.
It goes much further than that.
Way further. The physical surface of this single star would stretch all the way out, swallow the entire asteroid belt, and consume the orbit of Jupiter entirely.
It is a physical scale that completely defies our everyday intuition. When you start dealing with stellar objects of this magnitude, the human brain really struggles to map that kind of geometry.
It really does. And that is the exact mission of our deep dive today. We are looking at a celestial object known as VY Canis Majoris.
A truly legendary star in astrophysics.
For sure. And we've gathered a massive stack of source material for you today. We've got astrophysical data, historical observation records dating back over 2 centuries, and some, frankly, truly stunning 3D mapping derived from the Hubble Space Telescope.
The Hubble data is just incredible.
It's mind-blowing. But our goal today isn't just to gawk at a really big star. We want to understand how a star this chaotic actually functions on a mechanical level. How does it physically shed its own mass into the void?
And what its imminent spectacular death tells us about the life cycle of the universe itself.
Exactly.
What's fascinating here is that VY Canis Majoris isn't just large. It is profoundly unstable.
Right, it's not a calm giant.
Not at all. In astronomical circles, you'll sometimes hear it referred to as Betelgeuse on steroids.
That is a terrifying nickname.
It really is. It's classified as an extreme, oxygen-rich red hypergiant or red supergiant, depending on which specific metric a researcher prioritizes, and it is currently pushing the absolute theoretical limits of the laws of physics as we understand them.
Okay, let's unpack this, because when we say large, we need to put some hard numbers to that visualization we just did with Jupiter.
Right, we need the actual data.
According to interferometry data from the Very Large Telescope, VY Canis Majoris has a radius that is approximately 1,420 times that of our sun.
Let that sink in for a second.
Yeah, 1,420 solar radii.
And we should clarify what that actually means in 3 dimensions, because radius is just a line from the center to the edge.
Right, just a one-dimensional line.
Exactly. When you translate that 1,420 radius into a 3-dimensional sphere, the math becomes staggering. The volume of VY Canis Majoris is almost 3 billion times the volume of our sun.
Wait, billion with a B?
Billion with a B. 3 billion Earth suns could fit inside it.
I was trying to find a way to ground this in reality, so think about it this way. If our sun was like a standard 12-inch classroom globe sitting on a desk in your living room.
Okay, a nice tabletop globe.
Yeah. VY Canis Majoris would be roughly the height of a 14-story building.
It's absurd to think about.
It's just this monolithic structure looming over your entire neighborhood. It's so big that if you were an object traveling at the speed of light, which is the absolute speed limit of the universe, roughly 186,000 miles per second, it would take you a full 6 hours just to circumnavigate its surface once.
6 hours at light speed.
Yeah. For context, if you wanted to go around our sun at the speed of light, it takes about 14.5 seconds.
That speed of light metric is crucial, though, because it highlights the physical problem this star faces.
Being too big.
Exactly. Being that large comes with immense structural consequences. It brings us to a concept in stellar astrophysics known as the Hayashi limit.
Right, because a star can't just keep growing forever. The universe has rules. But what exactly is the Hayashi limit keeping in check?
Well, to understand the Hayashi limit, you first have to understand how a star survives day to day.
Okay, how does?
A star is essentially a million-year-long wrestling match between 2 fundamental opposing forces. On one side, you have gravity.
Pulling everything in.
Yes, the sheer mass of all that plasma and gas wants to pull everything inward, crushing it all down into the core. On the opposing side, you have radiation pressure.
Meaning the energy from nuclear fusion, right?
Correct. Deep in the core, atoms are smashing together, releasing unimaginable amounts of energy in the form of photons light.
Okay.
As these photons bounce their way out toward the surface, they physically push against the plasma. That outward push is radiation pressure.
So it's like a balloon inflating while gravity tries to squeeze it.
That's a perfect analogy.
Mm.
When those two forces are perfectly equal, gravity pulling down, light pushing up the star is stable. We call that state hydrostatic equilibrium.
Hydrostatic equilibrium. Got it.
And our sun is currently in a very comfortable state of hydrostatic equilibrium.
I'm guessing VY Canis Majoris is not comfortable.
Not at all. Because it is so incredibly massive, the gravitational crush at its core is extreme.
Right.
So to avoid collapsing, the core has to burn fuel at a ferocious rate, which produces a staggering amount of outward radiation pressure.
Just to fight off its own weight.
Exactly. This outward force is so intense that it literally pushes the outer layers of the star further and further out into space, bloating the star to that 1,420 solar radii.
Which is why it's so huge.
Right. But here's the problem. The further those outer layers get from the core, the weaker the grip of gravity becomes.
Oh, because gravity falls off with distance.
Exactly. The Hayashi limit defines the theoretical boundary, like the maximum size a star can reach while still maintaining that balance.
And if it crosses it.
If it gets any bigger, the outward radiation pressure will just overcome the inward pull of gravity entirely, and the star will simply blow its own outer layers away.
So it's teetering on the absolute edge.
It is actively crossing the edge. It is barely holding itself together. The outward pressure is so strong that the star's surface gravity is incredibly weak.
Which is an amazing visual. Now, if you're listening to this, you would logically assume that a star this massive, taking up a volume of 3 billion suns, would be like the brightest thing in the night sky.
You'd think so, yeah.
You'd think you could walk outside, look up, and it would be this glaring beacon. But oddly, it isn't. You can't even see it with the naked eye. It demands a telescope.
It's a brilliant cosmic irony. I mean, we are talking about one of the most intrinsically luminous stars in the Milky Way galaxy, yet it is almost entirely hidden from our daily view.
Let's trace back to how humans actually figured out this thing existed, because it's been hiding in plain sight for a long time.
It has a fascinating observational history.
It really does. The first time someone officially jotted down a note about this star was a French astronomer named Jérôme Lalande back in 1801.
Yes, over 200 years ago.
He logged it in his star catalog as a 7th magnitude star.
Right, and we should probably quickly define the magnitude scale for context because it's a bit counterintuitive.
Yeah, the math is weird.
It dates back to ancient Greece, where they ranked stars from first magnitude, the brightest, down to 6th magnitude, which were the faintest stars you could see with the naked eye.
So the lower the number, the brighter the star.
Exactly. Or, well, I should say the math works out that way today. A modern first magnitude star is exactly 100 times brighter than a 6th magnitude star.
Okay, makes sense.
So when Lalande categorized VY Canis Majoris as a 7th magnitude star in 1801, he was saying it was just slightly too dim to be seen without a telescope under dark skies.
But for a telescopic object, 7th magnitude is still quite bright and easy to spot.
Very easy, yeah.
But if we look at the historical data, things get weird. Since about 1850, the light from VY Canis Majoris, as viewed from Earth, has actually been fading.
Yes, getting progressively darker.
It's getting dimmer and dimmer. And observers around 1847 specifically noted it as being a crimson star, like really deeply red.
A very distinct color.
Now, if I don't know anything about astrophysics, I hear that a star is fading and turning deep red, and I think, oh, the star is dying, the fusion engine is running out of fuel.
That is a very logical assumption, but it is completely wrong in this case.
Really?
Yes. The fading we observe isn't because the fusion engine inside the star is shutting down or cooling off. It is due to a phenomenon called extinction.
I hear extinction, I think dinosaurs. What does extinction mean in space?
In astrophysics, extinction refers to the blocking or scattering of light by dust and gas sitting between the light source and the observer.
Ah, so something is in the way.
Exactly. Remember the Hayashi limit? We established that the star's surface gravity is incredibly weak because it's so bloated, and its luminosity is violently pushing outward. Right. Because of this, the star is essentially blowing its own outer layers off into space. It has a massive stellar wind.
Like a cosmic fan.
Yeah. It is ejecting so much material that it is actively building a dense, dusty nebula completely surrounding itself.
So it's burying itself alive in its own debris.
That's a perfect way to put it. The dust shell around it is absorbing the visible light coming from the star.
Wow.
The light is still being produced with just as much intensity, but it's hitting this thick envelope of circumstellar dust and being blocked from reaching our telescopes on Earth.
So it's not actually turning off.
No, not at all. That's why it appears to be fading over the centuries. The wall of dust is just getting thicker.
And this dusty veil actually caused a massive headache for astronomers, didn't it?
Oh, a huge one.
Because in the 19th century, observers were looking at this fading crimson smudge, and they didn't think it was one single massive star.
No, they didn't.
The historical records show they thought it was a multiple star system. Some observers claim they measured up to 6 distinct companion stars orbiting each other. They thought they were looking at a cluster.
They did. And, if you put yourself in their shoes, looking through a 19th century refractor telescope, you can understand why.
Really?
Yeah. When they looked at that specific spot in the constellation Canis Major, they didn't see one smooth smudge. They saw multiple, distinct, bright points of light, all clustered tightly together.
I have to push back on this, though. Were 19th century telescopes really that prone to optical illusions? How do you mistake a cloud of glowing gas for 6 entirely distinct spherical companion stars?
Well, it's not just a limitation of the glass they were using, though that was part of it. It has everything to do with the specific physical properties of this nebula.
Okay, explain that.
This isn't a smooth, uniform bubble of gas like a soap bubble. The material being ejected by VY Canis Majoris is fiercely clumpy, chaotic, and asymmetrical.
Clumpy.
Very. So imagine a light bulb surrounded by a very patchy, thick cloud of smoke.
Okay, I'm picturing it.
The light from the central star escapes through thinner patches in the dust, and it brightly illuminates specific, highly dense knots of gas further out in the nebula.
Oh, I see.
Through a 19th century telescope, these brilliantly illuminated nodes of dense gas looked exactly like individual, distinct companion stars.
Wow, so the star was basically putting on a cosmic light show, casting spotlights on its own ejecta to trick us into thinking it had friends.
That is exactly what was happening. And this wasn't fully cleared up until surprisingly recently.
Yeah, the sources say it took a long time.
It took almost a century to definitively resolve the debate. It wasn't until 1998 that astronomers could confidently say there were no companion stars.
What changed in 1998? Did we just get better telescopes?
We developed better techniques to counter the Earth's atmosphere. They used high-resolution imaging and a technique called speckle masking interferometry.
Okay, speckle masking interferometry. Break that down for us because that sounds incredibly dense.
It sounds complex, but the concept is brilliant. When you look at a star through a telescope on Earth, the image gets blurred by our atmosphere. The air is turbulent, shifting the light around constantly.
That's why stars twinkle.
Right, exactly. Speckle imaging involves taking thousands of incredibly short exposures, fractions of a second, so fast that you essentially freeze the atmospheric turbulence in place.
Oh, like taking a super fast photo of a moving car.
Exactly. Each image looks like a random splatter of speckles. But by using complex mathematical algorithms, specifically Fourier transforms, you can combine thousands of these frozen speckle images to reconstruct what the object actually looks like without the atmospheric blur.
That is genius.
It really is. When they did this to VY Canis Majoris, the 6 companion stars just vanished. It became clear it was a single solitary giant throwing off a wildly complex reflection nebula.
So if the star is pumping out enough material to physically block its own light and trick astronomers for over a century, what exactly is inside that cloud of material?
A lot of very strange chemistry.
Right. What is it making? Because this brings us to the chemistry of the star, and the data paints a picture of a celestial body that acts less like a peaceful sun and more like an industrial cosmic smoke machine.
The scale of the mass loss is what truly sets it apart. The data indicates VY Canis Majoris loses about 5.6 times 10 to the negative 4th solar masses per year.
I need a translation for that math. What does that mean in Earth terms?
It means every single year, this star is losing an amount of mass equivalent to roughly 30 times the mass of the entire planet Earth.
30 Earths every year.
Every single year, just violently blowing 30 Earths worth of gas and dust out into the void annually.
That is insane.
This is among the highest mass loss rates known for any star anywhere. It's unusually high even for red hypergiant. And we finally got to see exactly how this is happening when the Hubble Space Telescope turned its gaze toward it.
The Hubble 3D mapping data, I loved reading this part of the sources.
It was a watershed moment in astrophysics. Combining Hubble's optical data with ground-based observations from the Keck telescope in Hawaii, astronomers were able to create a three-dimensional reconstruction of the star's surrounding envelope.
And what did it look like?
What they found contradicted older models entirely. They didn't find a gentle, continuous breeze of particles expanding outward in a perfect sphere.
Like the solar wind.
Right, it wasn't like that. They found massive, highly asymmetric, incredibly complex structures. The nebula is filled with distinct filaments, arcs, bows, and dense nodules of material.
And the timing of these structures is what's fascinating. By measuring how fast these arcs and bows are moving outward, astronomers can rewind the clock.
Yes, they can trace them back to the source.
The data shows the star suffered massive localized ejection events roughly 70, 120, 200, and 250 years ago.
No.
It's like it has a violent fit every few decades and just burps out a massive chunk of itself.
The mechanics driving this are chaotic. Let's compare it to our sun again. Our sun occasionally has coronal mass ejection solar flares. These are generally governed by a relatively well-behaved, globally structured magnetic field. But the mass loss from VY Canis Majoris is different. The jets and arcs observed by Hubble are randomly oriented, shooting away from the star at wildly different speeds and angles.
So it's just firing off in random directions.
Catholic. This points to localized, massive explosions occurring on active parts of the star's enormous surface.
Why are they localized? What's causing a specific patch of the star to just explode outward?
It comes down to deep, turbulent convection. Inside this star, massive convection cells, bubbles of hot plasma rising to the surface, cooling and sinking back down or churning violently.
Like boiling water in a pot.
Exactly like boiling water.
Yeah.
But in a star this huge, a single convection cell bubbling to the surface could be the size of our entire sun.
Wait, one bubble is the size of the sun.
One bubble. When these massive bubbles rise, they interact with highly complex, localized magnetic fields in the star's tenuous outer layers.
And then what?
The magnetic field lines get twisted and snap, releasing huge amounts of energy that blast that local material out into space.
It's essentially boiling over, and the bubbles are the size of stars. That is terrifying.
It is a violent environment.
But what it's boiling over with is where my mind really gets stuck, because we have spectroscopic data on this cloud. We know what molecules are in this nebula, and it is far more complex than just standard hydrogen and helium.
Much more complex.
Yeah.
For one, the star is a very strong emitter of what astrophysicists call astrophysical masers. Specifically, it emits hydroxyl, water, and silicon monoxide masers.
Okay, hold on. A maser, I know what a laser is. Light amplification by stimulated emission of radiation. Is a maser just a laser but for microwaves?
That is precisely what it is. Microwave amplification by stimulated emission of radiation.
But how does a laser or a maser naturally form in outer space? On Earth, we build high-tech laboratories with mirrors and power sources to create them. How does a cloud of gas do it accidentally?
It requires a very specific physical mechanism called population inversion, and the environment around VY Canis Majoris provides the perfect laboratory.
Okay, break that down.
You have a massive cloud of molecules. Let's use water molecules as an example. The central star is incredibly bright in the infrared spectrum.
Because it's a red supergent.
Right. This intense infrared light shines into the gas cloud and pumps the water molecules. It hits them with enough energy to push their electrons into a higher excited energy state.
So you have a whole cloud of highly energized, unstable water molecules.
Right, and they want to release that energy and return to their baseline state. When one molecule randomly drops back down, it emits a microwave photon.
Okay, just one photon.
Just one. But that photon travels through the cloud, strikes another excited water molecule, and forces it to drop down and emit a photon of the exact same wavelength and direction.
Oh, wow.
That creates a cascade. One photon becomes 2, 2 become 4, 4 become 8. The signal is amplified massively.
That's amazing.
The clump of material the star shed between 1985 and 1995 is the actual source of some of its most intense hydroxyl maser emissions. It is literally a naturally occurring microwave laser in space.
The universe building its own lasers is incredible. But here's where it gets really interesting to me. It's the chemistry of the dust itself.
Molecular makeup.
Yes. We aren't just talking about water. Spectroscopic analysis, which is analyzing the specific wavelengths of light absorbed by the gas to read its chemical fingerprint, has detected incredibly complex molecules in this nebula.
Very complex.
The sources mention titanium oxide, hydrogen cyanide, phosphorus mononitride, and get this, sodium chloride. NaCl.
Table salt.
Yes. The star is burping out table salt and water and titanium into the void. It is a dying star at the absolute end of its life, but it is acting like a chaotic, high-temperature factory churning out the basic building blocks of rocky planets.
It acts as the ultimate cosmic forge. The ratio of gas to dust in the envelope around VY Canis Majoris is around 500.
What does that mean compared to normal stars?
For context, that is about 5 times higher than typical red supergiants. This envelope has a total mass of up to zero point 0.4 solar masses of just pure ejected material hanging around it, making it at a temperature of about 800 Kelvin.
But this incredible, chaotic cloud of dust and complex molecules is a double-edged sword for astronomers. It's fascinating to study its chemistry, but that exact same dust makes the star itself incredibly difficult to measure.
That is the big catch, yes.
Which brings us to a massive controversy in modern astrophysics that the source material highlights. We need to talk about the red supergiant problem and the mystery of the shrinking star.
This raises an important question. It's a textbook example of how the very tools we use to observe the universe can sometimes mislead us if we don't fully account for the physical environment we're looking at.
Let's lay out the scale of the problem. Early estimates of VY Canis Majoris were completely off the charts. We mentioned earlier that its modern accepted estimated radius is 1,420 times the Sun.
Yes, the current standard.
But if you read astrophysics textbooks or articles from the late 20th century or even the early 2000s, they placed the star's radius at over 3,000 solar radii,
It was easily.
sometimes pushing 4,000. They estimated its luminosity at over 500,000 times the Sun. It was widely touted everywhere as the undisputed heavyweight champion, the single largest star known to human science.
The issue is that those early measurements suggested a star so exceptionally large that it actually violated the theoretical models of stellar evolution we just talked about.
The Hayashi limit.
Precisely. It was too big to exist to maintain hydrostatic equilibrium. According to the physics of the Hayashi limit, a star of that size should have immediately blown itself apart. It should have been physically impossible.
But then, modern observations specifically using an instrument setup called the VLTI, the Very Large Telescope Interferometer with the AMBR instrument, revised this dramatically.
It did.
They brought the radius down from 3,000 to that 420 solar radii and dropped the luminosity down to somewhere between 178,000 and 270,000 times the Sun. They essentially cut the largest star in the universe in half.
This raises a very fundamental question about astronomical observation. How did multiple teams of highly trained scientists get it so incredibly wrong for decades?
Yeah.
How do you lose thousands of solar radii?
Exactly. And if this dust is hiding everything, how did we ever figure out its real size? And why did the dust make it look bigger in the first place?
Well, the error stemmed directly from how that specific type of dust interacts with light. As we discussed, the thick circumstellar envelope absorbs the visible light from the star.
Right.
But physics dictates that energy doesn't just disappear. The dust grains absorb the starlight, they heat up tremendously, and then they re-radiate that energy outwards. But because they are cooler than the star itself, they radiate it in the infrared spectrum.
So the dust cloud itself starts glowing brightly in the infrared.
Exactly. Most of the energy output of VY Canis Majoris that actually reaches Earth arrives in the infrared spectrum, peaking between 5 and 10 microns.
Okay.
The earlier astronomers, who were trying to measure the angular diameter of the star to calculate its size, were heavily reliant on this infrared data because visible light was blocked.
Makes sense.
But their models failed to properly separate the boundary where the actual surface of the star, the photosphere, ended and where the glowing hot dust shell began.
Oh, I see.
The dust was so hot and so dense and opaque in the infrared that it artificially inflated the perceived size of the star. They were measuring the star plus its massive blanket of glowing dust, thinking the entire structure was the solid star.
Wow. So they were basically measuring the smoke, not the fire, and thinking the smoke was part of the fire.
That is exactly what happened. It wasn't until 2012 that researchers used high spectral resolution interferometry to carefully peer through the contamination of those circumstellar layers.
You mentioned the VLTI earlier. How does linking telescopes together help see through the dust?
The Very Large Telescope in Chile consists of 4 main telescopes. When you use interferometry, you physically link the light gathered from these separate telescopes.
Okay, like combining their power.
Exactly. By doing this, you create a virtual telescope with a mirror as wide as the distance between the individual telescopes. This gives you incredibly high angular resolution, the ability to see very fine details.
Oh, that's clever.
With this resolution, they could finally map the exact temperature profile of the object and calculate the star's size based on its Rosseland radius.
Okay, stop there. Rosseland radius. The text mentions this is the distance where the optical depth is 2/3. I read that and my eyes glazed over. What does an optical depth of 2/3 actually mean?
It's a very weird concept because we are used to planets like Earth that have a hard, rocky surface. You know exactly where the Earth ends and space begins.
Right.
Stars don't have a hard surface. They are giant balls of gas that just gradually get thinner and thinner until they fade into the vacuum of space. So astrophysicists need a mathematical definition of a surface.
Right, because otherwise where do you draw the line with the tape measure?
Exactly. Think of it like driving into a thick fog bank.
Yeah.
When you first enter the fog, you can still see the road ahead of you pretty clearly. The fog is thin.
Okay, sure.
But as you drive deeper, the fog gets denser until you reach a point where you can't see anything past your hood. The fog has become completely opaque to your vision.
I've been there. It's terrifying.
In astrophysics, optical depth measures how opaque a gas is to photons. The Rosseland radius, an optical depth of 2/3, is the mathematical point, where the gas of the star becomes opaque enough that photons can no longer easily escape without hitting an atom.
Oh, I get it.
It is the exact same mathematical condition we use to define the surface of our own sun.
So they basically used this high-tech virtual telescope to pierce the glowing dust, find the specific depth where the star's actual gas became a wall of fog, and measure that diameter.
Yes, that's exactly it.
And that's what gave us the highly accurate, though much smaller, 400 and 420 solar radii figure.
Correct. It stripped away the illusions of the dust.
Yeah. So scientists just got it wrong at first. Does this mean VY Canis Majoris lost its crown? Is it no longer the largest star?
It did lose the undisputed top spot. With the revised measurements, stars like UY Scuti, Westerland 1W206, and Stevenson 218 currently hold larger estimated radii in the modern catalogs.
Okay, so it got demoted.
Sort of.
Oh.
However, it's crucial to understand that the sizes of all these extreme hypergiants are notoriously difficult to pin down for the exact same reasons we just discussed.
Because they all have that smoke screen.
They're all shedding mass. They all have fuzzy, ill-defined boundaries hidden by dust. Even today, depending on what wavelength of light you use to look at VY Canis Majoris, you get a completely different size.
Wait, really?
Yes. For example, while the optical photosphere, the visible light surface, is 1,420 solar radii, if you measure its radiophotosphere using radio waves, it is calculated to be almost twice that size.
That is deeply mind-bending. The star is literally a different physical size depending on what kind of light you use to look at it.
It's all about how you observe it.
Because it's not a solid sphere, it's a gradient of glowing plasma and dust that slowly fades into the vacuum.
Exactly. And to truly understand the behavior of this isolated, chaotic giant and why it's throwing off so much material, we can't just look at the star in isolation. We have to look outward. We have to look at the neighborhood it calls home.
Right, because stars don't exist in a vacuum. Well, they physically do exist in a vacuum, but you know what I mean.
Yeah, they have environments.
They have astronomical environments. They interact with their surroundings. Let's look at the real estate of VY Canis Majoris. Where does this monster actually live in the galaxy?
It is located about 1.2 kiloparsecs away, which translates to roughly 3,900 light-years from Earth in the southern constellation of Canis Major.
Okay, so relatively in our neighborhood, galactically speaking.
Yes. If you were to look down at the grand spiral structure of our entire Milky Way galaxy, VY Canis Majoris sits on the outer edge of the Orion Arm, which happens to be the exact same spiral arm that our solar system is traveling through.
And it isn't just floating out there completely alone in the dark. The sources note it is physically associated with a massive structural cloud known as ESH-2310 and a young open star cluster called NGC 2362.
The astronomical observations of this specific region are beautifully dramatic. ESH-2310 is a massive molecular cloud, a sprawling, dark, cold nebula of gas and dust where new stars are actively being born.
Stellar nursery.
Yes. When we observe this region, VY Canis Majoris is projected right onto the tip of a bright-rimmed section of this molecular cloud.
Oh, like it's right on the edge of it.
Exactly. And we know they are connected because the vectors of velocity, the precise direction and speed the star is moving through space, match the movement of the cloud perfectly. There's a near certain physical association.
They are traveling together.
Right. And more importantly, we can clearly see the violent impact the star is having on its environment.
How so? What is a star that big doing to a cloud that massive?
We can track it through observations of carbon monoxide, or CO emission. Radio astronomers look at the edge of the molecular cloud bordering the bright rim near the star.
What do they see?
They observe an abrupt decrease in the normal emissions of carbon monoxide, accompanied immediately by an increase in brightness in a different, rarer isotope of carbon monoxide.
Okay, I'm going to need you to translate that for the non-radio astronomers among us. Why do we care which isotope of carbon monoxide is glowing?
Because different isotopes react differently to heat and radiation. The shift in these spectral lines indicates that the intense ultraviolet radiation and the massive physical stellar winds from VY Canis Majoris are slamming into the cloud.
Oh, wow.
The star is actively destroying the raw molecular material of the cloud and intensely heating the cloud's rim, altering its chemical composition.
It's like it's the loudest, most obnoxious neighbor moving onto the edge of the quiet galactic suburbs.
That's a great analogy.
It moves in, it's massive, it's aggressively burping out salt and titanium, and it's just blasting extreme radiation into a local stellar nursery, completely altering the landscape and burning away the local cloud structures.
It is violently reshaping its environment, pushing a massive shock wave into the gas. But this noisy neighbor is living on severely borrowed time.
Because stars like this don't last long, do they?
Not at all. Because of its massive size, it is racing toward an explosive conclusion.
Which brings us to the final act, the death of a hypergent. Because the one rule of the cosmos is that stars this big do not live long. You read about tiny, cool red dwarf stars that can theoretically burn their hydrogen for trillions of years, outliving the current age of the universe many times over.
Yes, red dwarfs are incredibly long-lived.
But VY Canis Majoris, the source text notes it is highly evolved but less than 10 million years old.
To put that timeline in perspective, our sun is about 4.6 billion years old and is only halfway through its stable life.
Wait, our sun is billions of years old and this thing is only 10 million.
Yes. VY Canis Majoris is less than 10 million years old, and it is already deep into its death throes.
Oh, why the massive disparity? That's such a short lifespan.
It all comes back to mass and gravity. Because it is so massive, gravity is squeezing its core so incredibly hard that the core has to burn through its nuclear fuel at a staggering, frantic rate just to produce enough radiation pressure to avoid collapsing.
It's burning the candle at both ends.
And in the middle, it started its life as a hot, dense blue O9 main sequence star. At that time, it was roughly 25 to 32 times the mass of our sun.
Okay.
And now, having exhausted the hydrogen in its core, it has bloated outwards, cooled down to become red, and is rapidly fusing heavier and heavier elements. The data suggests it is currently fusing helium into carbon en masse in its core.
And that phase is fleeting. The time a star spends in this red hypergenic phase is estimated to be between 100,000 and 500,000 years total. Astronomers expect VY Canis Majoris to meet its absolute end within the next 100,000 years.
Yes, very soon.
In cosmological terms, that's tomorrow afternoon.
It really is a blink of an eye.
So how does a beast like this actually end? Our sources present a couple of fascinating and quite terrifying options. Let's look at fate option A, the supernova.
This is the traditional expected outcome for a massive star. Because of its massive size, the core will continue fusing heavier elements, progressing rapidly from carbon to neon, then oxygen, then silicon.
Right.
But eventually, the core will fuse silicon into iron. Iron is the kiss of death for a star.
Why is iron different? Does it not burn?
Up until iron, every fusion reaction releases energy, creating that vital radiation pressure. Fusing iron absorbs energy.
Oh, that's a problem.
A massive problem. The moment the core turns to iron, the radiation pressure turns off like a switch. Hydrostatic equilibrium completely fails.
Yeah.
Gravity wins instantly.
It collapses.
In fractions of a second, the entire mass of the core collapses in on itself at an appreciable fraction of the speed of light, hits quantum density limits, and bounces outward, resulting in a catastrophic explosion.
A supernova.
Exactly.
Specifically, the data suggests VY Canis Majoris could result in a type IIP, a type N, or perhaps a superluminous supernova. Can you briefly differentiate those? What makes them different?
It depends largely on how much of its envelope it retains before the explosion. A type IIP, the P stands for plateau, happens if it holds on to a massive envelope of hydrogen.
Okay.
The explosion shockwave heats this massive hydrogen shell, causing it to glow steadily, creating a long plateau of brightness for months.
And the N?
A type 2, the N stands for narrow, happens if the star is surrounded by a dense, pre-existing circumstellar cloud.
Which we know VY Canis Majoris definitely is.
Exactly. In a Type 2, the supernova shockwave plows violently into that exact salty, dusty nebula we discussed earlier, converting kinetic energy into intense light.
Wow.
And a superluminous supernova is exactly what it sounds like, an explosion up to 100 times brighter than a standard supernova, potentially powered by a highly magnetic neutron star left in the center, or by extreme interactions with the surrounding mass.
And what's left behind after the dust clears? Like, what is the corpse of the star?
For a star of this initial mass, roughly 25 to 32 solar masses, the remnant core left behind after the explosion would almost certainly be too heavy to stabilize as a neutron star.
So it just keeps collapsing.
Yes. Gravity would continue to crush it infinitely until it formed a black hole.
So a giant, terrifying explosion, bright enough to outshine an entire galaxy, leaving a black hole behind. That's the Hollywood ending.
Very dramatic.
But the sources provide fate option B. And honestly, I think this concept is even more compelling. The second stage red supergent theory, resulting in what astrophysicists call a failed supernova.
If we connect this to the bigger picture, this is a relatively new and highly speculative area of astrophysics, but it addresses a major mystery.
A mystery. Like what?
Well, astronomers have long noted a statistical anomaly based on the number of massive stars we observe forming in galaxies. There should be a corresponding number of Type 2 supernovae happening.
Okay, the math should add up.
But there aren't. We mathematically see fewer supernovae than we should. Some massive stars seem to be just going missing.
And how does a star 3 billion times the volume of the sun just go missing? Like somebody misplaced it.
The theory draws comparisons to an observed object named N6946-BH1. This was a massive red supergent, very similar in its properties to VY Canis Majoris, located in a distant galaxy.
Okay, what happened to it?
Astronomers were monitoring it. It went through a few minor outburst episodes, got a bit brighter, and then it didn't go supernova. It just disappeared from visible light entirely.
Wait a minute. You're telling me a star that massive could just vanish without a supernova?
Yes.
I want you, the listener, to imagine staring at the night sky, looking at a bright, massive star, and one night it just turns off, like someone flicked a light switch. How does the physics of a failed supernova even work?
The hypothesis is that the star's core collapses directly into a black hole without triggering the massive outward explosion of a typical supernova.
But how? Where does the energy go?
It all comes down to neutrinos. As the iron core collapses, protons and electrons are crushed together to form neutrons. This process releases an intense, unimaginable burst of neutrinos.
Neutrinos, ghost particles. I was always taught they barely interact with anything. Like trillions of them are passing through my body right now and I don't feel it. How do ghost particles collapse a star?
It's not about them physically hitting things. It's about Einstein's most famous equation, EMC squared.
Yeah.
Energy and mass are interchangeable.
Okay, right.
In a core collapse, there are so many neutrinos packed so densely, carrying away so much energy from the core, that they actually carry away a measurable percentage of the core's mass.
Wait, really?
Yes, this neutrino burst effectively lowers the gravitational mass of the star's core by a tiny fraction of a percent almost instantly.
So a burst of energy literally evaporates a chunk of the star's mass.
Yeah.
And because the mass suddenly drops...
The gravity suddenly drops.
Yes.
Exactly. The outer envelope of the star, that 1,420 solar radii of bloating gas, was balanced against the previous amount of gravity. It suddenly feels a sharp drop in the inward pull.
Oh, wow.
This sends a relatively weak shockwaves outward that gently blasts off the loose outer envelope of the star, that dusty nebula we've been talking about. But the vast majority of the star's mass, it doesn't explode outward. It simply vanishes silently into the newly formed black hole at the center.
So instead of a blinding flash of light that outshines the galaxy, you just get a relatively quiet burp blowing off the outer shell, and the central star itself is just swallowed entirely by its own core.
Exactly. Just quietly falls into a black hole.
That is haunting. It means black holes might form far more quietly and frequently than we originally assumed.
It absolutely does. Now, there is also further speculation in the data about a different path.
Oh, there's a third option.
There's a chance VY Canis Majoris might not die as a red supergent at all. Remember those localized convective bubbles we talked about?
The ones the size of the sun?
Yes. The high ratios of the carbon-13 isotope in the star's ejecta suggest extreme internal churning, what astronomers call dredge-ups. Material from deep inside the fusion core is being mixed all the way up to the surface.
Because it's boiling so violently, it's dragging the heavy ash from the core up to the skin.
Yes. And this extreme mass loss could actually strip away so much of its outer hydrogen envelope over the next few millennia that the hotter, deeper layers are exposed to space.
Oh, peeling it like an onion.
Exactly. If it sheds enough mass, it could evolve back into a hotter blue star, specifically a Wolf-Rayet star, before finally detonating.
It's like it's trying on different outfits for its own funeral.
That's one way to look at it.
But no matter which path it takes, supernova, silent black hole collapse, or stripping down to a Wolf-Rayet, the end is near, and it will be profound.
The physics dictate it cannot survive much longer.
Okay, we've covered an incredible amount of ground on this deep dive. Let's synthesize this journey. We started with a star whose physical volume is 3 billion times that of our sun, a star so bloated it would swallow Jupiter.
A truly incomprehensible scale.
We explored the limits of physics, how it is literally ripping itself apart to maintain balance against its own fusion engine. We detailed how violent convection events burp out massive clouds of salt, water, and complex molecules, creating naturally occurring masers.
Space lasers.
Space lasers.
Yeah.
We saw how this smokescreen tricked astronomers for a century, forcing us to use virtual telescopes to pierce the optical depth of its fog just to find its true size.
The red supergiant problem.
Right. We looked at how it aggressively bullies its galactic neighborhood on the edge of the Orion Arm, and we traced its dark future hurtling toward either a violent galaxy-bright death or a silent collapse into the void of a black hole.
It serves as a phenomenal, real-time case study in the absolute extremes of stellar evolution.
So what does this all mean? Why should you, sitting here listening to this deep dive today, care about a volatile ball of gas 3,900 light years away?
It's a great question.
You should care because massive stars like VY Canis Majoris are the ultimate forges of the universe. All that chaotic mass loss we observe today, the table salt, the titanium, the carbon that is the star literally seeding the empty cosmos with heavy elements.
Providing the building blocks.
Exactly. The iron that carries oxygen in your blood right now, the calcium that hardens your bones, the carbon that makes up the spine of your DNA, all of those heavy elements required a massive star exactly like this one to live, to forge those heavy elements deep in its core under immense pressure, and to die, scattering them across the galaxy to eventually coalesce and form planets and oceans and people.
We are, quite literally, made of star stuff, as Carl Sagan famously said. And VY Canis Majoris is showing us exactly how that stuff gets made, baked, and violently distributed.
And we want to leave you with one final, awe-inspiring concept drawn from our source material to ponder on your own tonight. Let's say VY Canis Majoris does take fate option B.
The failed supernova.
Right. It suffers a core collapse into a black hole, it dies a failed supernova, and simply vanishes from the visual spectrum. It just turns off.
Okay.
The text suggests that even in this silent death, the collapse could still produce a highly focused gamma ray burst from its poles, and it would definitely fire an invisible shockwave moving outward at thousands of kilometers per second.
A shockwave of pure energy.
Yes. I want you to imagine that invisible wave hurtling out from the newborn black hole. And eventually, a few months or years later, it smashes into that massive, complex, salty nebula the star spent the last 1,000 years building around itself.
Oh, wow.
When that shockwave hits the dust, the friction and kinetic energy will cause that dust to glow brilliantly. It will light up the sky for decades, long after the star itself is entirely gone. An echo of a ghost.
That is a beautiful image.
It makes you wonder, is stellar death really an end? Or is it just an incredibly violent act of creation?